Is full. Well, good evening, everyone. Welcome to the April 2018 edition of the Big Bear Valley Astronomical Society virtual lecture series. Before we get started, I'd like to say we're truly honored to have a couple of quite esteemed guests this evening. We have our director from the Big Bear Valley Astronomical Society, Wenda Chow, with us this evening.
Not the Big Bear Valley Astronomical Society.
Not
the Big Bear.
Big Bear Solar Observatory, whatever.
Yeah, promoted.
Too many hats. Okay, sorry. You just got promoted to another
Oh
directorship.
boy, are you going to be president now? I can give it to you.
And we also have with us Dr. Valentin Pillay, the director of the National Solar Observatory. And I think I got that one correct.
Very good.
And we're equally honored to have with us this evening, for our speaker this evening, Dr. Frank Hill. Frank Hill is the director. I haven't been able to find an up-to-date bio on you, so I'm winging it a bit. I believe you are
Associate Director.
Associate Director of the NISP, which is a nested acronym that stands for the National Solar Observatory Integrated Solar Program. Synoptic Program. Sorry.
It's okay.
And I knew that, too. Synoptic, okay. Well, Frank received his PhD from the University of Colorado in 1982 and began his career with the National Solar Observatory shortly after that, and has been with the observatory since then. So, after that very brief introduction, some of it even true, please join me in welcoming Dr. Frank Hill.
Thank you, everybody. Of course, you realize that what Claude just told you means I'm pretty old. Anyway, that's okay. I'm going to be telling you about what we are doing here at Big Bear. We are installing an instrument called SOLIS. And before I go much further, let me just say, if you have a question, don't wait. Ask when you have the question, because if you're like me, you'll never remember it by the end of the talk. So, this is about the collaboration with Big Bear. You can see a bunch of logos there. You can go to the next slide, please.
Yes.
Yep.
Okay, are you there?
Yes.
Over here.
Do you hear us?
Yeah, I can hear you. Sorry, I realize now I actually have to do my own slides here. Hang on.
Oh. No, we can't advance them for you.
Yeah, no, that's okay. Okay, so there's a lot of letters, a lot of acronyms on you, as you can see on that first page. So I thought first we do is go through and just tell you what all these acronyms mean. They're all organizations. NSO is the National Solar Observatory. We're operated by AURA, which has a cooperative agreement with the NSF. AURA is the Association of Universities for Research in Astronomy. It's a big consortium of, I believe, on the order of 40 to 50 universities at this point who are involved in management of the big observatories for nighttime and for solar in the U.S. The NSF is the National Science Foundation. That's where all the money comes from. Most of it. Some of it comes from other places as well, but the bulk of it comes from the NSF. NSO has sites right now in Boulder, Colorado. The headquarters are there. And in Maui, Hawaii, that's where the DKIST is. The DKIST is the Daniel K. Inouye Solar Telescope. It's a 4-meter off-axis telescope, of which the Big Bear, the Goody telescope, is a smaller version, basically, in some sense. We recently transitioned from having 2 other sites in Sunspot, New Mexico, and Tucson, Arizona. We are now more or less completely out of those, and in our new homes in Boulder and in Maui, where the telescope is being built. NISP, as Claude said, is the Integrated Synoptic Program for NSO. It has 2 components to it. One is SOLIS, the one we'll be talking about tonight. SOLIS stands for the Synoptic Optical Long-Term Investigations of the Sun. And the other one is GLON, the Global Oscillation Network Group. You also have a GLON site at Big Bear as well, but we're really not going to talk about GLON tonight. The transition from having sites in Sunspot and Tucson to sites in Boulder and Maui required that we relocate SOLIS from its original location on Kitt Peak and then down in Tucson. And so we selected Big Bear because it has consistently good daytime seeing has a high sunshine fraction, it's a current glowing site, it's a premier observing site for solar, and a premier group of people running the place. So that's the background of the alphabet soup. Let's go on to the next slide. Taking the opportunity for a drink. You should be seeing now an image of the sun, a schematic of the solar structure. Some of this is going to be introduction. So I apologize for the experts who know all this stuff, but I think it's best to review these things. So this is a cutaway of the sun. Again, we are not talking about everything on this picture. We're not talking about the inside or helioseismology. We're not talking about prominences. But we are talking about the photosphere, sunspots, the chromosphere, and the corona. So those are all places you can see on the sun. The photosphere and the chromosphere are layers of the solar atmosphere. Photosphere is where most of the light comes from. Chromosphere is where some of the light comes from, particularly H-alpha light, which is a red color. Sunspots you can learn more about in a minute. The corona, of course, is the tenuous outer atmosphere that we all live in here on Earth. Next slide, please. Good?
Yes.
Okay, so what does SOLIS do? What does this instrument do? Well, it measures the magnetic field in the photosphere and the chromosphere. It also, that's one of the primary things it does. It also measures the disintegrated light from the sun, the spectrum of that, as if the sun was a distant star, single point source. So we actually do what might be considered to be more or less analogs of nighttime observing with this instrument on the sun during the day. So the light is integrated down over the entire disk, and the spectrum of that light is then analyzed. It also provides intensity images in several wavelengths as well. Next one. So why do we want to measure the solar magnetic field? Well, this is the most blatant reason why. These are pictures of sunspots. I'm sure you've heard of these. These are probably the most familiar solar phenomenon that everybody in the world knows about. They have a long history going back. They're first seen in China around 800 BC, as far as we know. There's an 11-year cycle of the sunspot number that was first noticed and established in the 19th century by Schwabe and Wolf. And then in the early 20th century, Hale, over at Mount Wilson, not too far away from Big Bear, found that the sunspots are actually regions of very strong magnetic field, on the order of 2,000 to 3,000 Gauss. Your fringe magnet is about 50 to 100 Gauss. So they're quite a bit stronger magnetic fields, and of course they're enormous. And these are active regions that produce flares, which are explosions produced when the magnetic field reconnects very abruptly and catastrophically. Also, active regions can be the source, not the only source of coronal mass ejections, or CMEs, which you may have heard of also, because they get talked about in the news a fair amount. And something called space weather, which is basically what happens to the Earth when coronal mass ejection material and flare material, various energetic particles and radiation hit the Earth. We are protected by a magnetic field of our own, as you probably all know. That's how compasses work, of course. But when it gets hit by stuff from the sun, that magnetic field can shake. It can disrupt the upper atmosphere, known as the ionosphere, and it can produce, particles can get trapped in the magnetic field and come down to the Earth's atmosphere and produce, of course, aurora, which are beautiful, beautiful things. But space weather can also adversely affect our modern technology. GPS, communications, power grids can all be adversely affected. Satellites, astronauts, military equipment, all these things can really be unhappy during certain space weather events. So the study of the solar magnetic field, which is the ultimate cause of space weather, is very important just for our day-to-day lives. In addition, of course, there's a very, very big intellectual scientific question, which is just how are cosmic magnetic fields in stars and planets, for instance, generated? Why is there a magnetic field at all in the Earth or in the Sun or in other stars? And of course, that's a big question. The answer is usually said, oh, it's a dynamo, and of course that doesn't really help explain anything. So there's really a lot of interest in measuring the solar magnetic field. Let's go on to the next slide. So this is maybe familiar to a lot of people. This is the what's called the butterfly diagram, which shows the location of where sunspots emerge throughout the course of the solar cycle. The top row shows you shows all the locations of the sunspot emergence going back to 1880. At the bottom is the actual number of spots on the sun as a function of time. You can quite clearly see, of course, the 11-year cycle in the bottom plot and in the top plot as well. And you can see that the sunspots erupt at high latitudes at the beginning of the cycle, and then as the cycle goes on, they emerge at lower latitudes. And this has been going on for quite some time. A lot of effort is spent on trying to predict this pattern, what's the next one going to look like, because again, for space weather and also for understanding the magnetic field generation, the dynamo itself. A lot of people try to predict the solar cycle, and I have to say that most everybody fails. On average, we get it right. But any single prediction, if it's right, is probably just by luck, in my opinion. Let's go on to the next slide, please. Let me have a sip of water here. So this now is another picture. Again, you can see the butterfly diagram here, but instead of just the locations of the sunspot, these are actual magnetic field measurements in the two polarities of the field, positive or negative. And then the two polarities are color-coded, and now you can see there's yet another additional layer of complexity to the solar cycle. It's not just that every 11 years you get this butterfly pattern. It's every other cycle, the pattern, the polarity, the colors flip. And you can see that starting on the left, you have on the top wing, you have a yellow polarity, which is positive in this case, and then it switches to blue, and then yellow, and then blue. So there's really a 22-year cycle of the solar magnetic field when you take into account the polarity. Another thing you can see on this plot is these strips, the diagonal strips that emerge from the butterfly wing, from the active latitudes, the active regions, and then go up towards the pole. The equator of the sun, by the way, is through the middle of the diagram. The upper part is the northern hemisphere, and the lower part is the southern hemisphere. But you can see that there's a process that is moving the magnetic field away from the active areas and up towards the poles, where you see this alternating yellow and blue pattern again. The magnetic field is transported up to the poles by a north-south flow of material in the sun. It's called the meridional flow, and because of the way that the active regions are tilted, and because of the fact that the polarity of the active regions flips from cycle to cycle, this transport basically cancels out the previous field of the poles of the sun and replaces it with the opposite polarity. And that stays there for the rest of the cycle until the next cycle shows up and begins the process all over again. So it's pretty complex system, and so far things have not been adequately explained by most of our theories. You may also see something that's kind of interesting in this particular plot. The strength of the polar fields, how intense those yellow and blue areas are at the top, are fairly highly correlated with the strength of the subsequent cycle coming up. So in other words, in the middle you see a strong yellow area, and the next cycle was also fairly strong. Then there's a weakening. You can see the blue for the next cycle is a little bit weaker, and that cycle was weaker. That's cycle 24, the one we are in now. But the curious thing is, you don't see much of colors of any kind after that. So what does this mean for the next cycle? We're not sure, but there is some indication that things are changing fairly radically in the sun and maybe affecting the overall cycle, maybe entering into what's called a grand minimum. You can find cycles of amplitudes covering many decades in the sunspot number, and I'm sure you've all heard of the famous Maunder minimum in the 17th century, when for 75 years or so there were no visible sunspots as far as we can tell. Is that coming up again? We don't know. We really have no way of telling, but it's interesting to follow this stuff, of course. Okay, questions at this point, or?
No hands raising.
Okay. I can't see, but actually what I have my image of you guys is kind of small right now, so I can't really see too well. Let's go on to the next slide. So I think, I hope I've convinced you that it's a good thing to measure the solar magnetic field, that we want to do this. We learn a lot, and it can impact your day-to-day life. Your cell phone may not work because the sun did something. Okay, so now let's ask how we want to measure the solar magnetic field. How are we going to do that? Well, in general, any physical conditions that we measure in the sun or any other star is done looking at the intensity of the light as a function of its wavelength, how long the waves are. And we do this because photons that are generated inside the sun, eventually, after a long period of time, maybe a million years, they reach the photosphere, the surface of the sun, and there they encounter atoms of various elements that have all congregated up there. So the light, when it hits some of these atoms, it's absorbed and it's re-emitted again, but the intensity has certain wavelengths determined by what the element is. Is it iron, or carbon, or oxygen, or helium, or whatever? And also the local physical conditions, the temperature, the density, the velocity, magnetic field, and other things as well. So this produces a set of lines, dark lines in the solar spectrum, which is, you can really, is pretty analogous to a barcode. And if we go to the next slide, you'll see that barcode. So this is actually data taken at Kitt Peak many years ago with the Fourier transform spectrometer of the entire visible spectrum, from infrared at the top down to the UV at the bottom. And you can see lots of little black things in there. Some of them are fatter than others, but there's a lot of them all over the place. Those are the spectral lines, and they contain all the information that we ever get about the sun, the physical conditions on the sun and on the stars as well. So that's the basic input for all of solar observing. Let's go to the next slide. And I'm afraid this is going to be one of the more technical ones here. So how do we measure magnetic fields, which is what we're after in this case? So if you have an atomic transition, you have a photon hits an atom, and it excites it, and the electron moves from one level to another, and then drops back down and emits a photon again at a certain wavelength. That transition, what the magnetic field is around, it actually produces three spectral lines. This is called the Zeeman effect, and it produces a splitting of the line, which I'll show you a picture of in a minute. If the field is large enough, if that splitting is larger than the width of the spectral line itself, then you can actually resolve all the components of the line, and you can easily measure it almost with a ruler, just by measuring what that is in angstroms, and then using the equations to get the magnetic field from that. That doesn't always happen. That has to have a strong field, a couple thousand Gauss or so, and most of the sun is not at that field strength. Luckily, the light is also polarized by the field. Polarization is when the plane of the vibration of a light wave is confined to a certain direction, or moves with a circular motion, as opposed to being randomly distributed in all directions. Then you have polarized light. If you have, when the fields are relatively weak, then the polarization, as a function of the wavelength lambda of the light, you can measure that polarization, and then you can analyze that to estimate the field. This is done with 4 parameters that are called Stokes parameters. Stokes was the physicist who worked this out. They're called I, Q, U, and V. I is the intensity. It's a simple line profile that I'll show you a picture of in a minute. V is circular polarization, and then Q and U are the two opposite directions of linear polarization. You can to get the field, magnetic field. You can get the projection of the magnetic field onto the line of sight between you and the sun from if you just have I and V, without Q or U. So that is something that's been done for a very long time now in solar physics. There's many line of sight longitudinal magnetographs out there, but it doesn't have the full information about the magnetic field that we really need. What we really need and want to do is to use all four of those Stokes parameters to get the full vector field. In other words, get not only the strength of the magnetic field, but the direction it is pointing in. So that is a key thing, and that is one of the things that SOLIS does. Now that was a pretty intense slide. Any questions on this right now, or is it clear as mud to everybody?
I'm lost.
Okay, well, let's try again. Ask a question.
I have a question.
Sure.
I'm not sure if it's a stupid question, but
That's okay. There are no stupid questions.
the what do you call it?
Magnetic
Spectra.
field?
When
Oh,
I look at a spectral line, it doesn't look like the one you showed me, the ones I've seen. But
is that because normally you just see a single
a
strip with
single
some?
one.
Yeah, that was just because in that previous slide, if you had all the way from the red to the blue, it would extend extremely long. So
Oh,
they
I
just
see.
stacked
So
it up
was
to.
just stacked?
Yeah,
Oh,
yeah,
okay.
to
I've
make
never
it.
seen it like that.
Oh, it's on a slide.
Yeah, I showed you that if you go back, you can see that slide. That's all the spectral lines in the visible that we have. You may have seen just a small section around one of these lines,
Yes.
and you probably saw a line drawing of it, perhaps. Looks like an upside down. I don't know. Well, it's an upside down peak of some sort. You'll see them in a minute here in the next pictures.
Yeah, so from here, just think of the upper left-hand corner
Yes,
being in the infrared, then go
Wow.
across.
So
Think of it
it's-
like reading sentences in a book, but it comes along until you go.
Lots of spectrums.
So it's an extremely long spectrum stacked up.
Right. Yeah, chopped up and stacked up. All the information we get, it comes from analyzing in detail the shapes of many of those little black lines and splotches in that picture. All right. Does that help?
Sort of. Does that spectral graph show many elements?
Yes.
Okay.
Now, if you go.
Okay, so yeah, I've looked at them in
Yeah.
isolation then.
Well, if you go back one more time, for example, the hydrogen alpha line that we're all familiar with is that line there. Sodium those two lines there are caused by sodium. A lot of these lines are iron, so everything is represented in there.
Okay, wow. Yeah, I've never seen it like that.
In the visible, anyway.
Shebang.
There's more parts of the spectrum, but we're just concentrating on the visible here. Okay. So let's see. Okay, let's go now. We've done how the solar magnetic fields are measured, the text, right? Let's go to the next slide.
We are there.
Okay, so you see measuring the solar magnetic field with some grayscale pictures?
Yes.
Yep.
Okay, right. So these panels here, on the left is basically an intensity picture of a sunspot. You can see a sunspot there, part of a sunspot. And I hope you can see a dashed line that is cutting through that image. Okay, it looks like Claude is pointing at it. Okay, now the next one over is the I spectrum, the intensity spectrum. This probably may look more familiar to you. This is just a little chunk of the spectrum around two iron lines, 6301 angstroms and 6302 angstroms, along that line that is drawn on the left. You can see the sunspot, the dark part of the sunspot known as the umbra, is cutting across the spectrum, the I spectrum, and then surrounding it is the penumbra, the lighter, dark gray, And if you look particularly on the right-hand line, 630.25, I hope you can see that the line splits. It broadens out and splits into three components, which is the Zeeman splitting that I referred to. Can you see that? Is that clear?
Yeah.
Comes out quite well.
Okay, good. The other three, Q, U, and V, are those other three crazy Stokes parameters, and they have very different characteristics, as you can see. They also have very, very small amplitudes compared to the actual intensity itself. And they have very characteristic patterns of white and dark, and they cross, and they broaden and cross and do all these things, and it's those details which tell us everything about the solar magnetic field, analyzing those patterns in these particular types of spectra. Let's go to the next slide. And now this is the same, similar thing, only these are just line cuts across the actual images of the spectra you saw previously. So there's I, which again, this is the same spectral region, 6301, 6302 spectral line, and there you can see the spectral lines that are probably familiar to you while looking at spectra in astronomical applications. Then you see, of course, Q, U, and V again, and again you see that they have their own characteristic behaviors and shapes. They go positive, negative in various places, and the separations of those, the widths of those features, the heights of them are all information that tells us about how strong the magnetic field is, and in this case, what direction it's pointing, and things of that nature. I don't know if you can actually, I can barely see it myself, but the numbers, the y-axis numbers, the intensity numbers are on the order of 30,000, 3 times 10 to the 4, whereas the other three spectra are on the order of 10 to the minus 5. So this is...
Uh-oh. What was that?
Well, I might be.
Something happened on our end. You dropped out for a moment. Are you back with us?
Put another quarter in the machine.
Okay, am I back?
Yeah, you seem to be. I don't know what that was. It might have been a bandwidth warning or something.
It said something about Windows Defender.
Oh. Is it time for updates?
I think I'm a virus, which is not too far off. Anyway, you can see the very large, like 9 orders of magnitude between the signal in the I spectrum and the signals in the other three. And so that makes, these are very small little changes. Means you have to do a really good job measuring the spectrum, and you have to really do a really good job analyzing the data in order to get some results out. So it's a challenge to do this. Okay, let's go on to the next slide here. I wanted to also mention that another aspect about the magnetic field of the sun is that it changes as a function of height as you go up in the solar atmosphere. So if you have an active region in the photosphere, the active region field, the magnetic field, is primarily directed perpendicular to the solar surface, or vertical. Am I still there? Or?
You're kind of there.
Oh, you froze again.
Oh, okay.
Okay, I think you're back again. Your
Okay.
volume broke up there for a moment. Sorry.
Okay. Your image has been fine on my end. So.
Okay, so
Continue?
I think we're ready to continue. I think we're back again.
Okay. So in the photosphere, the field in an active region is primarily vertical with respect to the surface, so perpendicular to the surface. But if you go higher up into the chromosphere, which is where H alpha is formed, by the way, there the field in an active region is primarily parallel to the surface. It's primarily horizontal. There is apparently this canopy of the magnetic field that changes from vertical to horizontal as you go up. Then observing the chromospheric fields very thoroughly.
Trying a direct connect here to the...
That's okay. I'm waiting.
Looks like this cable will not reach. We're going to have to stay with the Wi-Fi. Sorry.
What about going around the other side of the podium?
I don't think that's going to
It
reach.
still won't
How about a
reach?
beeline through the table?
Or through the table, yeah?
Does that reach? Almost.
Almost.
Where was your?
So
Now
close.
he's leaving Earth's orbit now.
The
so
mountain
we're-
to the
On this side, of course.
Almost there.
Have you ever what is Wi-Fi?
Okay.
Okay, so we just stretched a hard wire to the internet, so we're no longer going via video. I mean, Wi-Fi.
Wireless Wi-Fi.
Hopefully that will give us good signal.
Sorry.
And it's really stretched tautly across the room here.
Don't forget.
Okay, I think we have you back. Sorry about that.
Okay, that's okay. So let's see. So the magnetic field in active regions of the chromosphere is mainly horizontal, not vertical. But we have not really studied chromospheric fields. Right? We're good?
Yes.
Yep.
We have not studied chromospheric magnetic fields nearly as thoroughly as we have photospheric. We are just now beginning this, and in fact, SOLIS is the first instrument that's actually going to be doing chromospheric magnetic field observations on a routine, continual basis for a long time. So it'll be the primary source of chromospheric magnetic field observations in the future. It's important to know what these fields are. One reason is we need to extrapolate the field of the magnetic field of the corona, where a lot of space weather activity occurs, and at this point we cannot measure the field of the corona because it's just too weak, and the light is too dim. The corona is too dim an object to provide enough signal to see the magnetic field. So we have to rely on extrapolations of the field of the corona. As you can imagine, this has a lot of work and uncertainty in it. By improving the boundary condition of the chromospheric field, we should greatly improve the extrapolations. And we do this by using different spectral lines. So that gives us the field at different heights in the solar atmosphere. Okay, let's go on. So that's how we measure the magnetic field at a certain point. But then, of course, we do this at many spatial points on the solar disk. And then the polarization data is inverted. It's a mathematical technique to produce a magnetic field. And it pulls estimates into a magnetogram image. And we make a time series of the magnetograms. And we can then use a set of those magnetograms obtained over a solar rotation, which is 25 to 30 days, depending on where you are on the surface of the sun. You can combine those into something called a synoptic map, which purports to be a picture of the solar magnetic field around the entire sun in a given instant, but it's a blatant lie. And I'll explain that to you in a minute. So let's take a look at what these things look like. Let's go to the next slide, please. And this is a magnetogram, a longitudinal line-of-sight magnetogram observed in the 6302 line with SOLIS back in 2007. And you can see some active regions, black and white big spots there. Those are active. There could be a sunspot in there. And most of the sun at this point is gray or sort of a salt and pepper color. A pattern which is just basically the weak fields and the quiet sun that are everywhere. These regions where the sunspots are called active regions because that's where, of course, activity occurs, flares and some CMEs, not all of them, etc. The next slide shows you an example synoptic map where we have taken 28 days or so, 30 days worth of magnetograms and remap them to a coordinate system that was placed on the sun way back in the 19th century by a man called Carrington. The magnetograms are reprojected into this coordinate system, and then they're et cetera, to make these pictures of what purports to be the global field of the sun at a given instant. The problem with this is it took 27 days to get this data because we had to let the sun rotate underneath and get snapshots of what the magnetic field looked like on the front. And so on the right side of the image, that data is 28 days older than the data on the left side of the image. And the sun's magnetic field certainly changes much more rapidly than on a timescale of 28 days. So these maps are fiction. Nonetheless, we use them in many ways for various studies of the sun's magnetic field and where the solar wind comes out and things of that nature. But this is one of the major issues facing solar physics. It's just lack of coverage of the entire sun. There are ways now where we're beginning to really talk about throwing out all sorts of small spacecraft all around the sun in order to observe it, but we're probably still a long way from that. That would finally give us a real picture of the real sun's magnetic field at a given instant. No? Okay, let's go to the next slide. And now finally we're going to get to SOLIS. So SOLIS has, it's a single equatorial mount. It has 3 telescopes on it. It has the vector spectromagnetograph, the VSM, has a 1/2 meter aperture. This is the major workhorse of the set. And measures magnetic field, the vector magnetic field. We have a 14 centimeter full disk patrol instrument, which provides intensity images, currently in just a couple of wavelengths, but it will do it in several down the road. And then we have the gigantic 8 millimeter integrated sunlight spectrometer, which obtains the spectrum of the sun as a star. Actually, the entire visible, we chop it up and use 9 wavelength regions. This is all continuing the more than 40-year record of synoptic data, particularly magnetic field data that we have at NSO. Next slide. This is what the thing looks like. This is what it looked like when it was up by Kitt Peak. It was on top of a tower that Claude knows very well, 130 feet tall. By the way, Claude, that thing is slated for demolition soon. So, yeah. Well, you know.
Don't listen, Teresa.
The NSF has to knock down, has to show to the world that they can demolish something. This is it. Anyway, so there you can see the VSM, the ISS, and the FTP all mounted on the equatorial mount, which is not really visible here, but you'll see some better pictures of it. Let's go to the next slide. And this is an actual set of VQU and I spectra, like I showed you previously, from SOLIS itself now this time, as opposed to the other ones, which were highly processed. So this is pretty much raw data from SOLIS. So there's V at the top, Q, U, and then I at the bottom. The intensity is spectrum at the bottom. So that's the raw data that comes out. And then after much processing, if we go to the next slide, here are the magnetograms that we get out. So on the top left is the longitudinal magnetic field line of sight in the photosphere. The next one is the vector magnetic field, again in the photosphere. And then we have the chromosphere, but this is not a vector one. This is actually a longitudinal magnetic field map in the chromosphere using the core of the, using the wings of the spectral line. And below it is the same thing, only using the core of the spectral line. Core gets you high up, and wing gets you deep down. So there's a little bit of height variation just from those two, and there's a lot of height variation comparing these chromospheric magnetograms to the photospheric one over here. The chromospheric data is taken in the calcium 854.2 nanometer line, which is formed up in the chromosphere. And then in the bottom center is just the intensity of the sun in that particular line, in the wing, and then we have another line that we don't use so much right now, and I won't be talking too much more about it. The 10830 line in the chromosphere, the equivalent width, which is actually a good proxy for X-rays from corona. You also see that we have some boxes drawn around the vector magnetic field active regions in the center top image. Let's go to the next slide. And here's what we do in those areas. here's where we we do a full analysis to get the actual real vector field out of the data. So there's one active region that has been selected there, as you can see. At the top on the left is the magnetic field strength. What is the strength of the field? And then there's the inclination and the azimuth, the direction angles of the field there. Inclination is basically with respect to the surface. So the zero inclination is vertical. And then azimuth is which way the field is pointing in the east, west, north, south direction. We use a four-color coding of those directions to give a sense of what the field is doing. You can see from the inclination, it's black on one side and white on the other. And that means the field is coming up on one side and down on the other. So that's just the different polarities of the sun. And then you can see there's a complicated azimuthal structure here. Okay, let's go to the next slide now. And this is one you need to blink here. This is going to compare the photospheric field with the chromospheric field. So why don't you just blink them there. And I hope you can see that, particularly on the left side of the image, there is quite a distinctive difference. There's looks like a more blurring of the field somewhat, and it gets a little bit more diffuse. You can also see a little bit of shift of the whole field because the data was taken half an hour apart and the sun rotated. Those features are because the chromospheric field is primarily horizontal, and it's at the limb of the sun that you can see the horizontal field. You cannot see it at the center of the disk, but only near the limb. And so that is the effect that is causing that sort of blurring effect, blurring at the edge of the sun. So, okay. Any questions at this point?
Did everybody follow that about the azimuthal versus the inclination before? Okay.
All right, let's see. So the next slide, we can skip over this pretty quickly. This is just actually getting all the vectors for the field of the chromosphere. And you can see that we've done the inclination, azimuth, etc., and overlaid on a picture of the intensity of the sunspot vectors, which show the direction of the field. Just to demonstrate that we can actually do a vector magnetogram in the chromosphere in an active region. The next couple of plots are now what the integrated magnetic field of the sun, how that behaves, integrated over the entire disk as a function of many years. The first one is the full disk, the net flux, so it's an algebraic average for positive and negative values. You can see the solar cycle shows up as an increase in the amplitude of these quantities on the left and on the right part of the diagram. The next one probably looks more familiar. That's the unsigned flux. It's a total flux. There you can clearly see the solar cycle, the increase of the magnetic field during solar maximum on the left and right sides of the picture. One of the more interesting things is what happens at the polar field. As I said, the polar fields are indications of how the next cycle is going to be, how strong it will be. So if you bring up the next plot, which shows you the polar mean radial field, two blue and red lines or fuzzy lines. Those are the polar fields above between 60 and 75 degrees latitude. Red is the north, blue is the south. And you can see the polarity reversal occurring around 2013. This is a function of time. And you can see that the red field and the northern field and the blue field have now flipped the polarities. And at the moment, they look a little bit weaker than what they were previously, so that's a suggestion that the next cycle will be a little bit weaker as well. The next slide just shows you the same thing, only smooth to get rid of a lot of those small fluctuations. So just shows you a clear view of that. And that's pretty much what the magnetic field story is with SOLIS and the VSM, and we're going to turn now to the ISS to talk about some of the things it can do. Are there any questions at this point on the magnetic field?
Just one. When you measure the magnetic fields, do you have to wait for the sunspot to move from the center to the edge to get all the different measurements?
Were you able to hear that?
Yes, I heard that, yes.
Okay.
You don't have to, but we do, because we want to know how the sunspot is evolving, how it's changing, what is happening in the magnetic field as that occurs.
Well, I got the impression you could only measure some of the magnetic fields when it was on the edge as opposed to the center.
Well, you can, because the sun is a sphere, if you look at the center of the disk, you are sensitive to things that are oriented vertically towards you, okay? If you look at the edge of the sun, then you are sensitive to things that are, again, oriented towards you, but because the sun is a sphere, they're horizontal on the limb, and vertical in the disk center. So in order to see that geometry, you have to, you're right, you have to track the sunspot across the entire disk passage in order to sort that out. Does that help?
Yeah, so you also have kind of the same issue as that other plot where things are 28 days or whatever different.
Yep. Yes. The solar magnetic field is changing constantly, all the time. So, you know, it's tricky business to thoroughly characterize it. I don't think we've actually succeeded in that. Anything else? Okay. Yes. No.
I don't
Okay.
see any more
Next slide.
hands.
Oh.
Okay,
Okay. ISS. You got the
ISS. We're on the ISS now.
Okay, yes, we are leaving the VSM and we're going to the ISS. ISS stands for the Integrated Sunlight Spectrometer. It integrates all the solar light over the entire disk, so the spectrum is as if the sun was a distant and unresolved star. Okay, so then this provides activity indices. For one thing it does is it gives you activity indices that you can compare with other stars. You probably know about the Wilson survey over at Mount Wilson. That it found many stars have activity cycles, and that was all done on the basis of an index, a spectral index in the K line, the calcium K line. And so we can do the same thing now. We have been doing the same thing now for the sun in order to compare the sun with the other stars in those sorts of studies. You can also use it to measure differential rotation. Excuse me, which is kind of curious. And it turns out that this is of great interest to people who do exoplanet studies. And I'll address that in a minute or so. Let's go on to the next slide. And these are the 9 spectral bands that we are standard observing windows for the ISS. We have, starting from the top left, 388.4 nanometers, that's a CN bandhead. Then we have the calcium K line, the calcium H line. These are, as you probably know, very, very broad spectral lines in the solar spectrum. We have carbon 1, 5380, magnesium 1, sodium D line, the first D1, H alpha, the same calcium line we use for the chromospheric magnetic field, and then the 10A30 line as well. Those are just 9 sections that we have chosen. We actually have, we could if we wanted to keep the entire spectrum, but it's just not, these are the sections with the greatest interest. With the calcium K line, there are little bumps and wiggles in the core of the line, and people spend a career out of measuring those up and following what they do as a function of time and trying to learn about the thermodynamics of the chromosphere, for instance. If you go to the next slide, you can see a set of 9 of these activity indices that are all over, that are used by people. They have various names. These little bumps and wiggles in the core line have been named with fantastic names like K3, K2, K2R, K2B. Sounds like you're climbing a mountain in the Himalayas, but that's not really it. Anyway, so those are what some of the activity indices look like over the lifetime of SOLIS. And if you go to the next slide, here now we've combined the SOLIS observations with other measurements of this emission index that were done at SAP peak starting back in the mid-70s. So we have 4 cycles of this very precise measurements of this emission index. By comparing this with similar measurements, though none of them are this high quality for more distant stars, we can do a lot of comparative analysis between activity indices, rotation rates, and dipoles.
Frank?
Yep.
There are several points that are well off the curve. Is that due to noise, or are those significant?
Well, some of them are. I would say they're not the sun. They're the instrument. So there are noise. I see a set of measurements in the early days that all look like they were taken at the same time and have quite a range of values. I'm guessing that was some sort of instruments.
But if you look over to the right there, particularly there's one that's way off the cluster of the others. And
Right.
I don't know if that's a cloudy day or was that something.
I couldn't tell you precisely about that day, but it sure looks suspicious. I agree. I don't think that's the sun. But this is one of the challenges of of scientific analysis. What is an outlier? There's an outlier. What is it? Is it of interest? Is it noise?
Something to white out. Something just to white out.
Yeah, something, yes. Well, and you have to be careful about that. You know the story of the 12 micron lines, right?
Yes.
Okay, be careful. Okay. So another thing that can be done with the ISS is the next slide, which shows you that we can actually measure differential rotation. So by taking a time series of these and looking at one particular point and doing basically a wavelet analysis, which shows you frequencies as a function of time, you get these patterns using the calcium K measurements. They're split up into bands that correspond to various periods, which you can read across the top. There's the very strong feature that you see at around 28.6 is the major rotation rate of the sun. And you can see that it's not constant because as you go down in time, you can see that the frequency, the period is wandering around and changing a bit. Plus you see all other periodicities at other times as well. The reason that the major rotation rate appears to change is because as time goes on, basically you're tracking sunspots with this method, and the sunspots are moving to lower latitudes where the rotation rate is higher, and so that gives you the change in the rotation rate as a function of time. I find it intriguing what those other lines are. I don't think we know, but they look awfully significant in some way. But anyway, that's another thing that can be done with ISS data. Okay, next slide. I just wanted to mention that ISS is a good thing for exoplanet work. SOLIS is unique because it has both disintegrated spectra and spatially resolved magnetic field observations at the same time and from the same place. So that means you can develop models that relate the two. What sort of magnetic field pattern gives you what sort of ISS spectral signature. And because it's the spectral signatures that exoplanet people have to analyze, they can then use those models to estimate the stellar magnetism and the activity and try to assess what the potential impact might be on nearby planets. So ISS and SOLIS data has gotten very popular in the exoplanet world. Okay, next slide. We're getting to the end, folks. The FTP I have not much to say about because the FTP has not actually been fully developed. It's a focus control. It makes 2K by 2K intensity images at H alpha and 10/830 at the moment. It can run at a very high cadence, 10 seconds. So it can pour out a lot of data. We have a tunable visible filter that has been constructed by Jack Harvey. That's been done. It works. We will be installing it after this instrument is up and running at Big Bear. It still needs a fair amount of work. Also, we don't have a good flat field for it. So that's why there's only one slide for this particular.
Have you decided what lines will be used on that?
We have, it's completely tunable. It depends on the pre-filter selection. We have spots, I believe, for 6 pre-filters. We have not selected which those pre-filters are. And I think that you guys, that Big Bear is going to have quite a bit to say as to what those pre-filters might be when we get to that point. So, but you know, if you want to change, you can swap out pre-filters to get a different spectral range if you want, because the filter itself is tunable over the whole visible range. Okay, now we're going to finish up with SOLIS actually at Big Bear. The site is at the east edge of the property. The equipment is sitting right outside there. You probably saw it on the way in. Big white boxes and a big tarp thingy. We have our permit to do the whole site development. We're working on the final design of the site layout, the roof drive system, utilities. We have to actually still get the specific permit to actually build the thing, build the foundation. But that should be gotten in the next week or so. And we expect the whole thing to be up and running again by the end of the summer, in August.
Is that going to be a manned install or a remote?
It's remote. It can be, SOLIS can be run remotely. We can run it from Boulder, or you can run it from the office building at Big Bear. So it will be a remotely operated system. Of course, when it breaks, and obviously we have to go over and work on it.
Mm-hmm.
Sorry, go ahead.
By the way, you'll be pleased to hear that the eaglet flew out of the nest this morning.
Yay! Thank you. That's good, isn't it? The next slide just shows you a satellite view, Google Earth, which shows you pretty much where it's going to go. You can see the causeway there, and then the typical Google Map red lollipop sitting on the site where SOLIS is going to go. The next slide shows you an engineering drawing of what the site looks like. The mound is on the left. The corrugated thing is the roof that is will be driven with a motor, unlike its current state where it has to be pulled with a rope. That's actually taken a fair amount of time to design and get right, it turns out. The next slides are just pictures of the equipment leaving Tucson. You can see in the upper left the mount in the air, then the mount on a truck, then the ISS shelter. The ISS is in that box along with a lot of other stuff, computers being lifted. You can see the roof over there on the bottom right with the crane. Then the next set of slides, next set of pictures has the instruments, the 3 instruments, the FTP and the BSM have been put into one shipping container. The ISS is in its own container still. And then the next slide shows the stuff arriving at Big Bear back in January. So it's there. As soon as we get everything finalized and get the site built, it'll be installed and running. And so I'd just like to end here with a little summary. SOLIS is going to give you fundamental observations of the magnetic field, the integrated sunlight spectrum, full-disk intensity images. It's ushering in a new era of collaboration between Big Bear and NSO. There's already been a lot of collaboration from Gong and adaptive optics and other things, but this is going to be even more. And Big Bear is not going to be the source of the long-running synoptic magnetic field observations that we started way back in the 70s at Kidd Peak. So, thanks a lot for your attention. Any more questions? I hope there wasn't
I'll just talk.
more questions?
Yes, this is not going to be mounted on a tower like in Kidd Peak. What do you give up by giving up the tower?
Well, we don't give up too much, it turns out. The Kidd Peak was really important because the tower got us above a lot of the ground scene, but because you guys have a lake, that's done it for us. So we shouldn't. In fact, we expect to get better scene here at Big Bear than we ever got in Kidd Peak. So
if the lake ever fills up.
If the lake ever fills.
Well, I know, it goes up and down. I know.
Mostly it goes down.
Mostly down.
It goes up too. I've seen it go up. I've seen it go up.
Everybody points out, ever since I've been here, it only goes down.
Yeah.
There's I keep trying to point out there, that's not necessarily a causal relationship.
Yeah. Drink that much water?
I come from Tucson.
No, that's true, that's true. But the lake is extremely important. There was, in India, as you probably know, the Udaipur Solar Observatory was built by Arvind Bhatnagar, who was a student of Zirin. And he said, this is a good idea. I'm going to build one on a lake too. And so he did. The Udaipur one is on an island, not a causeway. It is actually completely surrounded by water. And because of a drought in India, we actually were able to get quantitative measurements of how much a lake improves things. So they measured the scene with no water in the lake, because there was a time when it was absolutely bone dry. And they measured it when it was filled also. And it turns out it's about a 40% improvement of the scene from a lake. So that's good to have.
Other questions?
One to John here, I guess. If we're 16 feet down now, can you quantify how much of a improvement or degradation we see from full lake?
We might be able to.
Well, you may be able to do that. I have I can only say anecdotally that I think that the scene now it's worse around noon than it used to be, because we get more local heating around the telescope that
Rocks
doesn't
and
get,
that kind of
Yeah, like
doesn't
100
get as
feet
much
out.
of a chance to get blown away.
It's just bare ground now.
And so at noon it's worse than it would get otherwise. Now, how much worse is it going to get? I don't know. I'd rather have it full.
I think to really measure it, what we'd need is a tower with scintillometers at a few different elevations.
Well, yeah, I don't know. The ATSC site survey guys have that. I forget what they found, but...
Well, I remember, because I kind of was involved with that. What we did was, we didn't have sensors on a tower. We had something called a Shabar, a shadow band ranger, which was a very clever instrument that had a number of photodiodes with different baselines that essentially measured the Fourier components of the scene at various heights, and from that you could back out what the scene was as a function of height. We actually calibrated it with a real tower with real thermistors on it in Boulder, and it agreed. So it worked fairly well. If I recall, Big Bear had an R naught of 7 or 8 almost all the time during the day, which was really good for something like the synoptic instrument of SOLIS. So,
I think we're a particularly good site for that kind of instrument.
exactly, right.
Other questions? Frank, would you?
One question, Claude, if I may. Where will be the day-to-day control for SOLIS? Is it here in
It'll be a big, where you are, Big Bear.
Yeah. What we'll probably do is we'll probably have a computer workstation like the one we have for Gong that's out in the control room.
Right.
And that's probably where
That'll be the SOLIS display.
That'll just be for SOLIS.
But SOLIS is going to take more hands-on than Gong does.
Yeah.
Just like there's 3 instruments, you have to watch it, things of that nature. We also will, Teacher Branson will be coming out to help, install, train, and be there for a while to get everything up and running. And he can also back up operating as well. So.
I almost thought you said Richard Branson.
Different person altogether.
It'll be nice to see Dietrich.
Yeah.
Yeah.
Can you say anything about the long-term plans as far as, I assume SOLIS will be around for numerous years. What are the long-term plans at the moment for Gong?
Well, actually, we are working on a plan to replace both of them. Replace SOLIS and Gong with a new network. We call it SPRING, the Solar Physics Research Integrated Network Group. And the idea, it would have a mount like SOLIS. In other words, it would be able to hold a number of different instruments. It would hold something that replaces the gong Doppler instrument, and it would hold a new version of the VSM or something like that. However, the key thing is it would both do multiple heights all the time. I mean several heights, like 10, to give us a really good look at what the magnetic field and the velocity field is as a function of height in the solar atmosphere. I think this is a key thing, particularly for helioseismology, which has a problem determining what the structure is underneath inclined magnetic fields, like you get in active regions and sunspots. This is not a good thing, and I think the way out of that is to study in detail the propagation of the waves through the atmosphere as a function of height and through the magnetic fields. So that's the idea, is to replace both SOLIS and spring, both SOLIS and GOM with spring. So we're working on that, and I expect
That's
if
another
we do manage
six.
to do that, it'll be about 5 to 10 years.
That'd be another 6-site network.
That's what I would hope for, at least 6, maybe even more, maybe 8. But also it might have different instrumentation at different sites, by which I mean you might not have a vector magnetograph at all 6, you might have a vector magnetograph at only 3 of them. Or you can think of even other things like maybe a coronagraph, at a few sites. So that's the idea.
Anything else? Well, if not, please join me once again in thanking Frank Hill for giving us a look into what is in the process of coming here to Big Bear. Thank you, Frank, very much.
Useful, not too confusing.
Well, this is good. A lot of the people in the room we volunteer as docents for the tours here at BBSO. And so now a lot of us will have more to say about SOLIS. And people say, what's that thing out there? Oh, that's SOLIS. That's